Now we're going to talk about adding and subtracting radical expressions. It's really important that you make sure that you do not try to add two radical terms together if they do not have exactly the same radical part. It's the same concept that you use when you are trying to combine like terms. You all are familiar with the fact that 2x plus 3x is 5x. Again, the reason for the reason that 2x plus 3x is 5x is from, what multiplication really is. 2x is notation that also means 2 times x. And what we know about multiplication is that it really is just generalized addition. So if you are asked to multiply some number by 2, you can get the same result by taking that number and adding it that many times. So multiplying x by 2 has the same product as taking x and adding it twice. So 2 times x is the same thing as x plus x. Similarly, if we have 3 times x, multiplying x by 3, that product can be found by taking x and adding it 3 times. So 3 times x is the same thing as x plus x plus x. And what we have then is now 5x's added, and using the same concept or the same rationale, adding x 5 times is going to give you the same thing as multiplying 5 times x. So using that same thought process works with radical expressions as well. If we are 2 root 3, that's notation for 2 times root 3, and multiplying root 3 by 2 is the same as adding root 3 twice. Multiplying root 3 by 3 is the same thing as adding root 3 3 times. And so 2 root 3's added plus another 3 root 3's added results in a total of 5 root 3's added. So the process that we use when we're trying to add or subtract radical terms is the same as for like terms. So if they have exactly the same radical part, again, both root 3's, then you can go ahead and simply add the coefficients together, and then you can leave the radical parts the same. So add the coefficients. 2 plus 3 is 5, and leave the radical part the same. And you get your 5 root 3 using that process. So can I simplify? And this word simplify, has basically different connotations in each situation you're working off of. You have to know what it means that when working with what a simplified expression is when radicals are involved. And when we're talking about adding and subtracting of radicals, this simplification, we would say that an expression that has radicals and that has more than one term is simplified if the radicals are simplified and also all of our like terms are combined. So this expression can be only simplified if either of these two terms would simplify. This root 2, our radicals, can only be simplified if, so a square root, this can only be simplified if this is a perfect square, or if this number is divisible by a perfect square other than 1. And so 2 is neither a perfect square nor divisible, so the square root of 2 cannot be simplified. Over here, the cubed root of 2. So in order to, this expression would only be, or this term would only be able to be simplified if, since I'm dealing with a cubed root, this number underneath, the radicand, would have to be a perfect cube, which it is not, or it would have to be divisible by a perfect cube, which again, it is not, other than 1. So does either term simplify? In this case, no, it does not. Okay? Neither of those terms will simplify. And the other consideration when trying to simplify a radical term, a radical expression with more than one term, can you combine the terms? And to combine would require that both of those terms have exactly the same radical part. This is a square root, this is a cubed root. You cannot combine because they are not the same. So this is no. If this were a cubed root and this were a cubed root, then you could do 2 minus 5, but because they are not exactly the same, you cannot combine. So, can I simplify? The answer to that is no. You can only simplify if either of the two terms will simplify or if you can combine the like terms. So can I simplify? No, you cannot. So this would be representative of the most simplified expression for what we have in this scenario. Let's look at another expression. We want to simplify 3 root 108 minus 2 root 50 plus 3 root 12 plus 98. Please note, these are not indexes of 3. They're not written up here, they're written out front. They are coefficients. So it's really 3 times the square root of 108. It is not the cubed root of 108. So in terms of doing my simplification, remember, it will simplify if any of these radicals can be simplified or if I can combine any like terms. So I'm going to work with the simplification of the radicals first. So 108, first of all, you think, okay, is there a number I can multiply twice to get 108? That answer is no, because 108 is not a perfect square. But it will simplify if 108 is divisible by a perfect square. So one of the methods that we were talking about before is just taking your number and listing all of the factors. So if I start that process here, I know 1 and 108 are factors. Because this ends in an even number, I know that it's divisible by 2. So I would be 2 and what? 108 divided by 2 would be 54. I know that 3 goes into 108. The divisibility rule for 3's are, if you can add the digits together and come up with a number that's divisible by 3, then the number itself is. So if I add these digits, 1 plus 0 plus 8, that's 9. And since 3 goes into 9, I know that 3 will go into 108. So 3 and 108 divided by 3, that would be 36. And you can keep on going, but I've come up with a number that is a perfect square. Okay? And I'm always looking for the largest. And since I know I've gone in order, 108's not a perfect square, 54 is not a perfect square, so 36 is the largest perfect square that goes evenly into 108. So doing my simplification, I know that I can write the square root of 108 as the square root of 36 times the square root of 3. So the square root of 108, the square root of 36 is 6, and so that is 6 root 3. Okay? Just another option that I want to talk to you about before we go on, an alternative for simplifying square roots, is to use a factor tree. And some people say you would want to go ahead and complete this factor tree until you have all of the prime factorization. But I kind of cheat a little bit when I'm doing this for simplification. I'm just really going to start until I can find some numbers that in this case would be a perfect square. So let's say you look at this and you say, oh well, I know 9 goes into 108, and you just start looking for any two numbers that multiply to 108. So if I multiply 9 by 12, I know if I multiply 9 by 12, I get 108. I'm going to write my factor tree this way instead. Instead of doing it in the traditional manner, I'm going to write it as a list of products. So I know that if I multiply 9 by 12, I can get 108. And I kind of like to stop myself. If ever I come across a perfect square, then I do say, oh, okay, that's a perfect square. So I'm just going to leave that alone, and then I'm going to mess with this number. 12, is 12 divisible by a perfect square? Yes, it is. It's divisible by 4. So I could write 9 times 4 times 3. 9 times 4 times 3 will also be 108. So using what we've done before, so the square root of 108 then should equal the square root of 9 times the square root of 4 times the square root of 3. I stopped because this number is not divisible by any perfect squares. So the square root of 9 is 3 times the square root of 4 is 2 times the square root of 3. And you can see doing it this way also gives me the same thing as before. The same thing as I had looking for all of the factors. So sometimes you're going to be working with really large numbers, and it's not going to be apparent, or really in your face obvious what numbers even go into this, let alone, what might be a perfect square. So sometimes it's nice to just kind of start. And let's say, I can do this again. Let me erase that. Let's say instead of starting with 9 and 12, let's just say I started with 2 and 54. Okay, so 108 is 2 times 54. And 54, let's say you recognize as maybe, I don't know, 9 and 6. Okay? So what we have is we've got one perfect square. That's not a perfect square, and that's not a perfect square. So if we write it like this, 2 times 9 times 6, or square root of 2 times the square root of 9 times the square root of 6, what we have here, we recognize that that's 3. And then what we've got here is 2 square root of 2 times the square root of 6, which we would have to put back together as the square root of 12. Okay? Notice what I have here is not exactly the same as what I have here, but they are equivalent. The issue with what I have here is that I've not simplified fully. 12, if you notice, or if you think about what goes into 12, 12 is divisible by 4, which is a perfect square. So when you're dealing with radical notation, if the number underneath is still divisible by a perfect square, you have not simplified fully, and you need to continue with your simplification process. So when I have my square root of 12, I can break that into 4 times 3, and the square root of 4 is 2. And so now I have the 3 times 2 root 3, which is my 6 root 3 up here. So there are lots of paths that you can take. It's just essential that when all is said and done, the radical expression that you give as your answer, or that you end up with, does have to be one that is fully simplified. The route that you take to get there can be varied, but the end result cannot. Okay, it has to be that you say 6 root 3 is the simplification of the square root of 108. So for 50, I can look at 50 and say, oh, that's divisible by 25, and I know 25 is a perfect square. What if you don't? What if you say, well, I know 5 and 10 go into 50, so 50 5 times 10, but here, I'm not seeing a perfect square, and even if I break this down, this 10, I have 5 times 5 times 2, I still don't have any perfect squares in my list, but we do have in our list 5 times 5, which is 25, and 25 is a perfect square. Okay? So when I'm asking you to simplify, if in your list of factors, if ever you have at least, so if it's a square root, if you have at least 2 factors that are the same, it will simplify, because obviously multiplying the same number twice will give you a perfect square. Okay? So this is the square root of 25 times the square root of 2, which is 5 root 2. So you can do that, using the 5 and 10, or you could just say 25 times 2. So we have now the square root of 50. I'm going to come back and rewrite. So this first term, the square root of 108, simplified to 6 root 3. And we still had this 3 in front. So 3 times root 108 is the same thing as 3 times 6 root 3 when we just rewrite the simplification for the square root of 108. So 3 times 6 root 3, the square root of 50 we found to be 5 root 2, so this is minus 2 times 5 root 2. Hear my dog barking in the background. Sorry. I'm going to erase that and give myself some more room here. Okay, and then now we're on the 3 root 12. So 12 is divisible by 4, so I'm going to just do it that way because I can recognize that 4 goes into 12. So that's the square root of 4 times the square root of 3, which is 2 root 3. So I have plus 3, this is my 3 here, and then this times the simplification of the square root of 12, which is 2 root 3. And then for the last term, 98, so, again, let's just say you're not really sure what perfect square goes into 98, but the fact that 98 ends in an even number, we know automatically it's divisible by 2. So we could multiply 98 by 2 and 49. And then once you do that, you should say, oh, that's a perfect square. So the square root of 98, I would break into the square root of 49 times the square root of 2. And the square root of 49 is 7. So the last term simplifies to 7 root 2. Okay, so now kind of putting all of this together, the 3 times 6 root 3, I'm just going to multiply. This is 3 times 6 times root 3 is really what we have. Multiplication of 3 factors. And what we know about multiplication is that it is both commutative and associative. So using the associativity property, I can go ahead and group. Since I have this times this times this, I can get that product by first multiplying the 3 by the 6. And for simplification purposes, I want to do that. So the 3 times 6 is 18. So this is 18 root 3. Here, multiplying the 2 by the 5, then I have minus 10 root 2. 3 times 2 is 6, so plus 6 root 3. And then here I have plus 7 root 2. So as we discussed, so all of that was just to get our radical simplified. When we're dealing with simplification of an expression involving radicals, and that expression has more than one term, we do have to not only simplify our roots, but we also have to combine any like terms. Looking at my 4 terms, these 2 terms have the same radical part as do these. So these 2 terms are like terms, and these 2 terms are like terms. So my last little bit here, combining my like terms, 18 root 3 plus 6 root 3. I'm adding, again, when you're adding like terms, you add the coefficients and leave the radical part the same. So 18 plus 6 is 24. So that's 24 root 3. Negative 10 root 2 plus 7 root 2. Negative 10 plus 7 is negative 3. So then we have minus 3 root 2. Finally, we are done. This expression is simplified because both of the roots are simplified and I have no more like terms to combine. So once you get to that stage, then you know that you can stop. And that's something that I hear most from students, especially when we're starting to work with these radicals, is they say, I just don't know when to stop. Okay? And so to know when to stop, you have to listen to these things that I'm telling you. When you are simplifying and you have multiple terms, you stop when you have an expression where every root is simplified, meaning those can't be, since we're dealing with square roots here, they have to be numbers that are not perfect squares themselves, nor are they divisible by perfect squares. And also you can stop when you've combined your like terms. Okay? That's the end for this one, but I want to go on to the next PowerPoint to continue adding and subtracting. So more adding and subtracting, multiplying and dividing. We're just going to go ahead with the addition and subtraction aspect for now. Go back to black and color here. So another example just like the one we did. So I've even put that, what I've been telling you about, when is it simplified? It is simplified if your radicals are simplified and all your like terms are combined. So when I give you something like this, you want to go through and look at your radicands first. So 28. So if I'm asking you simplify, or can you simplify the square root of 28? 28 is not a perfect square. In terms of, is there a number you can multiply twice to get 28? No, there are not. It's not. But is 28 divisible by some such number? And yes, it is. 4 is a perfect square that goes into 28. So the square root of 28 I would write as the square root of 4 times the square root of 7, because I'm always interested in factors of this number that are perfect squares. The square root of 4, the number that I can multiply twice to get 4, is 2. So the square root of 28 is 2 root 7. 63, let's say you're not sure what perfect square goes into 63. Let's just play around. And that's kind of how you have to do it. If you can't think about that perfect square, then you just have to start trying to break that number down. Let's say you can recognize that it's divisible by 3. And you would have to divide 3 by 63 divided by 3 is 21. And I'm not seeing any perfect squares, but I know I can break that 21 down some more. That's 3 times 3 times 7. Still, I'm not seeing any perfect squares. Everything is broken down, but remember what I was saying before. If you're trying to simplify square roots, if you're multiplying a number twice and multiplying a number by itself, you are going to create a perfect square, right? So that 3 times 3 in the list, that produces a perfect square of 9. So now I can see, oh, well, that's my perfect square. There is a perfect square that divides 63. So the square root of 63, let me write this up at the top. Is square root of 9 times the square root of 7. The square root of 9 is 3. So this is 3 root 7, just the square root of 63. And then for the last term, 7 is not a perfect square. And the only factors of 7 are 1 and 7. Yes, 1 is a perfect square, but we're not interested in that in terms of simplification. So, square root of 7, I cannot simplify this last term at all. So rewriting the beginning expression with my radical simplified, I have 7 times 2 root 7. That's my 7. Times my 2 root 7, minus 3 times 3 root 7, plus 16 root 7. So the 7 times 2 here is 14, 3 times 3 is 9. So I have 14 root 7 minus 9 root 7 plus 16 root 7. At this point, I have simplified all of my radicals. Last step, are there any like terms to combine? So we have a root 7, a root 7, and a root 7. All 3 terms have exactly the same radical part, so all 3 are like terms. And to combine like terms, I just add or subtract, depending on the sign, the coefficients, and then leave the radical part alone. So 14 minus 9 is 5, and 5 plus 16, I get 21. So the simplification of the original 7 root 28 minus 3 root 63 plus 16 root 7 is, what did I say, 21? 21 root 7. One more. 2 times the cube root of 81 minus 5 times the cube root of 192 minus 10 times the cube root of 3. So, trying to do simplification. Let's say you're not sure. So let's start playing around with 81 a little bit. See if we can come up with any perfect cubes or create any. Come come upon any in the breakdown or create any when we look at all the factors pulled apart. So 81, most of you recognize as being 9 times 9. Now please, again, we're looking for cube roots, not square roots. So I'm trying to find, well, first of all, you would say, is there a number I can multiply 3 times to get 81? No, 81's not a perfect cube. Then we say, well, we also have to see if 81's divisible by a perfect cube. So right now I'm going to start playing around with the factors of 81. So I've got it broken down to 9 times 9. Neither of those are perfect cubes. I'm going to break them down some more. This is 3 times 3, as is the other 9. So what I have now is 3 times 3 times 3 times 3. So none of those factors individually is a perfect cube. But I know that if I multiply the same number 3 times, that I make a perfect cube, right? So if I multiply the same number 3 times, 3 times 3 times 3, I will get a perfect cube, and that perfect cube is 27. So I've discovered a perfect cube, 27, that divides this 81. Okay? So this is, I'm going to rewrite this as the cubed root of 27 times the cubed root of 3. The cubed root of 27 is 3. So this part here, right, or when we're talking cube root, we're saying, what number do I multiply 3 times to get this? Well, obviously, that number is 3. So we have 3 times the cubed root of 3. Let's work on our 192. I'm going to get this out of my way so I've got some more room. You can just use your paper, use the extra right side of your paper to do some work here. So 192, it ends in an even number, so I know it's divisible by 2, so I'll just start there. So 2 times what? 192 divided by 2, that would be 96. I don't recognize either of those as being perfect cubes, so let's try to mess with the 96 some more. 9 and 6, so that must be divisible by 3. We could go with the 2 again if we wanted to as well. I'll just go with the 3, so it'd be 3 times, what, 32? Again, I'm not seeing any perfect cubes in my list. So now I've got 2 times 3 times the 32. That's 8 and 4. And finally, I do have a perfect cube. So we could do 8 times 2 times 3 times 4. That would be, right, the remaining 2 times 3 is 6. 6 times 4 is 24. So if I come up here and I write, so that's the cube root of 8 times the cube root of 24. The cube root of 8 is 2. Is it simplified if I write 2 times the cube root of 24? Is that, this is a simplification of this, but it's not fully simplified. Hopefully you know when you look at 24 that it's divisible by 8, and we've already talked about 8 being a perfect cube. Okay, so this would not be acceptable as simplification because it is still divisible by another perfect cube. So if you want, you know, coming back down here, so I'm just going to write this as 8 times 8 times 3. And I'll go ahead and up here and just write it as the product of 3 radicals rather than the standard 2. Again, like I've said, there's lots of ways to do this, but the idea is you're looking for every single perfect cube factor of that number. So we've got the cubed root of 8 times the cubed root of 8 times the cube root of 3. So erasing that, that was a simplification, the 2 times the cube root of 24, but it's not completely simplified. And that's what we're going for. When we say simplified, we want completely simplified. So the cube root of 8 is 2 times the cube root of 8. That's another 2. So this is 2 times 2 times the cube root of 3, or 4 times the cube root of 3. Okay, so cube root of 192, completely simplified, is 4 cube root 3. And then finally this last term, 3 itself is not a perfect cube, nor is it divisible by a perfect cube other than 1. And so I cannot do anything to simplify that last term. So rewriting, so I have 2 times 3 cube root 3 minus 5 times, so that's my 5, times the simplification of this, which is 4 times the cube root of 3, minus 10 times the cube root of 3. So this 2 times 3 is 6. This 5 times 4 is 20. And they're all cube roots of 3, so they're all 3 terms are like terms. So 6 minus 20 is negative 14, and negative 14 minus 10 is negative 24. So my final answer is negative 24 times the cube root of 3. Okay? So let me know if you have questions, especially if you're needing some extra help with the simplification. Finding and playing around with the factors so that you can find your perfect squares and your perfect cubes. Talk to you later.